Welcome everyone. We are going to talk about moments and center of mass in this video. So consider the following scenario. You have a rod on top of the fulcrum. This triangular thing is called fulcrum. And you are placing a mass of m1 here at the distance d1 from this point on the top of the fulcrum on the rod. And we have mass m2, distance d2. Yeah, we'll keep MKS system. So this is in kilograms. And D1 and D2 are measured in meters. Okay. So we have seen this scenario when kids play seesaw and stuff. We have seen balancing like that. I'm sure we have seen such balancing. So now the point is, the question is, when does this rod gets balanced? So for that, we have Archimedes' law of lever, which says the following. That says that the rod balances, the rod will balance when M1 D1 M1 D1 equals to M2 D2. So this is the point here. If this M1 D1 equals to M2 D2, then the rod balances. So let's try to see this again. So the idea would be, what would be coordinate of such a point where the rod balances, right? So let's have, again, we have a fulcrum here. There is a mass M1 at a distance x1 from this point. Let's call this point as x bar. And we have at x2, we have a mass m2. And then again, we are trying to see when there is balances. So now this distance is going to be then d1. This distance is d2. Now, so what is d1? D1 is going to be x bar minus x1, right? Distance between A and B is B minus A, right? Similarly, D2 is going to be x2 minus x bar. So again, using the law of lever from above, we get x bar x1 d1, sorry, m1 is equal to x2 minus x bar 2. So we can bring them on one side. So we have x bar m1 minus x1 m1. We have x2 m2 minus x bar 2. So now bring the ones with the x bar on one side, because we are solving for x bar. This becomes x bar m1 plus x bar m2 equals to x1 m1 plus x2 m2, and then divide both sides by, take x bar common. In bracket, we have m1 plus m2. This is going to be x1 m1 plus x2 m2. Divide both sides by m1 and m2. This gives me x bar equals to x1 m1 plus x2 m2 divided by m1 plus m2. So this is your center of mass. Center of mass. Here, m1, m2 is called the total mass. And x1, m1 plus x2, m2 is called the moment. All right, so now we have, so suppose we have three masses on a rod. Now we can have n masses, but let's work out with three masses now first. So we have, say, this is where my fulcrum is located at x bar. Then I have, say, m1 at x1, say m2 at x2, and m3 at x3. And the question is, what should be the position of this x bar so that the whole rod gets balanced, right? So again, using the same idea from the above, we get x bar minus x1 times m1 plus x bar minus x2 times m2 equals to x3 minus x bar times. Now, if we change the sign here and bring it on the other side, we get x bar minus x1 times m1, x bar minus x2 times m2 plus x bar minus x3 times m3. Or you can write this as summation I going from 1 to 3 of x bar minus xi times mi is 0. So now we can generalize this, in fact, right? So we have, if we have n particles instead of m1, m2, and 3 of weight m1, m2, mn, then the similar formula will look like summation I going from 1 to n of x bar minus xi times mi is equal to 0. Now let's multiply and open this up. So we have summation I going from 1 to n of x bar mi equals to, I'm going to open this up and bring it on the other side. So I have summation I going from 1 to n of xi mi. And now here from the first part, I can take x bar common. So we have x bar summation I going from 1 to n of mi is equal to summation I going from 1 to n of xi mi. Divide both sides by summation mi. So we have x bar is equal to summation I going from 1 to n of xi mi divided by summation I going from 1 to n of mi. So again, let's label what are these objects. So these, or what are these quantities? So this is my center of mass. This is my moment. And this is my total mass. All right, so now let's consider, let's consider a 3D, or sorry, a 2D version of this. Okay. So what is the idea? We have So we have basically three masses, say M1. So M1 is at say 3, 2. So let's say the weight of M1 is, so M1 is at 3, 2 with M1 equals to say 8 kilograms. Then we have M2, say at 2 minus 1. So 2 minus 1 and say M2 be 4 kilograms. And then we have M3 at minus 1, 1. Say M3 is 3 kilograms at minus. Okay. So now this is my X1, Y1. Here I have X2, X3, Y3. And this is my X2, Y2. Okay. Now we want to compute the center of mass for these three weights. So let's compute this. So how would we go about computing it? So what we'll do is we'll consider this, break it into X and Y coordinate. So we can assume that we have M1 was at, so we're going to write down the X coordinates, right? So M1 is at 3. We have M3, so this is my X coordinate. M2 is at 2. And M3 is at minus 1, but whatever related weights they have. So in that case, we have X bar is summation I going from 1 to 3 xi mi over summation mi I going from 1 to m, 1 to 3. Okay. So and similarly we will have y, same scenario for y as well. We have here we have m2 at minus 1. We have m1 at 2, and we have m3 at 1. Yeah, I'm just writing the y coordinates of each of those points. Yeah. In that case, I'll get my y bar is summation yi mi over summation. Okay, so note that this object on the top, this summation on the top will be called my, which is moment in y, and this is called mx. Note that in Stewart, the notations are changed. So when you're doing the Weber sign problems, then mx and my are changed notation wise, but at the end, this all works out. Okay. Okay. So now if I want to compute this, how would I go about it? Let's just compute. So m, which is my, let's call this as m, the total mass. So m is going to be, add these masses up. So we have 4, we have 3, m1 is 3, so 3, m2 is 4, and m3 is 8. So we get 3 plus 4, so 7, 7 plus 8 is 15. It's 15. Now let's compute mx. Again, a word of caution, in Weber in Stewart's book, mx and my are interchanged. So when you're doing Weber sign problems, you just interchange them. So we have mx is so So 3 times, so let's see. So what are the coordinates here? So we can say 3 times x3. Oh, or we can write m1 x1 plus m2 x2 plus m2. Let's just write it systematically. x3. In that case, m1 is going to be m1 is 3, right? So 3, sorry, x1 is 3, m1 is 8, m2 is 4, m2 is 4, and x2 is 2, and m3 is 3, but x3 is minus 1. And this turns out to be 29. Similarly, my is going to be m1 y1 plus m2 y2 plus m3 y3. So same, we get now m1 is 8 kilograms, so 8 times 2. m2 is 4, so 4 times minus 1 plus m3 is 3, so 3 times 1 by 3. And that's going to be 15. So we get x bar is mx by m, and y bar is my by m. And this is 29 over 15. Where is the other one? It's 15 over 15. 1, this is 1.9. What does it mean? If we join these points, so the center of mass of these three masses, right? You can choose to imagine the rod, or you cannot choose to imagine. You can think about no rod as well. So the idea is that you have 3 masses located at this. The center of mass is going to be 1.93 for the x coordinate, 1.93 somewhere, and y coordinate is 1. 1.93 for x, and y coordinate is 1. So we are here somewhere. Sorry, x coordinate is 1, right? We have this case. So let's plot it. So 1, 0.93. So this is where the point will lie. All right. So now we want to go to this case we want to consider this scenario. Instead of basically point masses, we want to consider about a plate of uniform density. And then we're asking the same question: what is the center of mass? So for example, suppose I have we have the following plate here on top of fulcrum. This plate is filled in. Okay. So the question is now, okay, let's write down. So what are we considering? A plate of uniform density. The mass distribution is uniform. It's not that at one corner there's a big mass lump. You can think about this as basically take a plate which is of equal thickness everywhere, right? If you take a same metal plate, then it will be of uniform density, right? So consider a plate of uniform density rho, and then the question is, what is the center of mass? Of mass. Say, call it X bar, Y bar, and this will be also called centroid. So, for centroid is somewhere here. So this is my center of mass. And also called centroid. Okay. So this is where our integration will come because we have a continuous distribution. We don't have a discrete object. So let's try to deal with this. So we have the following. So we place our object like that. Suppose this thing is my plate of uniform mass. I situate it between A and B like that. And then I'm going to break this into some number of intervals. We have x1, x2, x3, x4. Now we are going to make rectangles similar as Riemann sum. So you can choose rectangles. Now the question is, what is the base and the height of this rectangle, right? So what we can do is the following. So let's take, we're going to make the rectangle. So let's try to first let have, so we'll take midpoint of x0 to x1, call that as x1 bar. Take between x2, x1 and x2, call it x2 bar. Take between, this will be x3 bar, and this will be our x4 bar. Now, let's draw the rectangles. And the rectangles will be drawn with the height as given by f of x1 bar. So we go on top here. Become clear in a minute why is that the case. This is my first rectangle. Similarly, second rectangle is going to be here. Similarly, I get third rectangle. And I get my fourth. Okay. So now let's write down. So let so we do what delta x is p minus a by n. So mi be the mass of Ri. Yeah, so each of these rectangles are Ri. My R1, for example. That's going to be rho times the area of Ri, right? And that is going to be given by rho times delta x times f of xi. Now let Ci be the centroid. Centroid, or the center of mass for or of Ri. Now note that this is interesting. So Ci bar So if I take a rectangle and the uniform, so this rectangle is of uniform density, then the center of mass is going to be halfway. So it's going to be half of this and half of that, right? So this is X, then and this is Y. Center of mass is going to be at X by 2, Y by 2, right? And that's because this is of uniform density. So our centroid is Xi, Yi for rectangle Ri, and that is going to be Xi bar. That's why we chose it to be the middle point. And Yi would be half of the will be half of this, right? So it'll be somewhere here. So Yi is going to be f of Xi bar. That's my Yi. Yi is f of Xi here. Yi bar rather. So I am going to divide that by 2. So this is a scenario. This is what is happening here. So this is halfway. And here we have M1. This is also halfway. We have M2. These are my centers, right? So we have C1, my C2 is here, my C3 is here, and so on. Okay. So therefore, the moment of Ri in X is going to be in X is given by the formula earlier. So we have summation I going from 1 to n of xi mi, which is going to be summation I going from 1 to n xi r. Now area, so mi was given by rho delta x f of xi divided by, so this is the summation xi mi. Similarly, moment of Ri's in y is summation I going from 1 to n of yi mi. Going to be summation I going from 1 to n. Now yi is half of f of xi bar rho delta x f of xi. Okay. So now that will give me mx is limit as n goes to infinity, right? These are approximations. So to get exact mx, we take limit as n goes to infinity of this summation I going from 1 to n of xi mi, and that is going to be limit as n goes to infinity of summation I going from 1 to n of xi bar rho f of xi bar delta x. And now this looks like a Riemann sum, right? So this is going to be integral a to b. So this will contribute to dx, and the rest can be written as x rho f of x dx. And similarly, we get my to be limit as n goes to infinity of summation I going from 1 to n of yi mi, which is going to be limit as n goes to infinity of summation I going from 1 to n of half f of x I bar square rho delta x, which is going to be integral a to b half, that half I'll bring outside, half f of x squared. Let me keep the rho out in front. So this is how we get mx and my. Now, what is my total mass? My total mass m is, so this is how we get mx and my. Now we're going to talk about the centroid. So let's talk about the centroid or the center of mass. We have m equals to total mass. It's going to be rho times a, because it's a uniform density plate. That's going to be rho. Area of a is going to be integral a to b fx dx. All right, so this gives us x bar equals to mx by m, which is integral a to b rho x f of x dx divided by integral m is total mass is rho a to b f of x. Now rho is common in both of them. The rho can get cancelled, right? Rho is a constant, it can come out of integral. And the bottom simply becomes the area. So we have 1 by a integral a to b x f of x dx. Similarly, y bar is going to be my over m, which is going to be integral a to b r rho f of x whole square dx divided by integral a to b of f of x dx. Again, we can cancel out rows, right? So rows get cancelled here and here. Rows will get cancelled here and here. So we are left with 1 by a integral a to b half f of x whole square. All right. So this is the idea behind the. Let's do one problem. So example. So find the centroid of the region enclosed by y equals to x, y equals to x, and y equals to. That's example one. Another example we are interested in is to find the centroid of a semi-disk or half disk of uniform density rho and radius. All right. So let's maybe work with this problem first. So we have a semi-disk of radius r. So we have a semi-disk. We have a semidisk of radius r, and the density is uniform. So let's call this as uniform density rho, right? So we have the upper part of this semidisk is given by y equals to square root of x square minus r square minus x square. Note that r is the constant. So this is my f of x. Now let's say, so let's find out, let's try to, we're going to find out x bar and y bar. So let's look at first integral a to b of x f of x dx. Because this is the integrand, right? We need 1 by a to b x f of x dx. So we already know a. Actually, we can calculate a using integral, but a is pi r squared by 2. I'll leave it that as a homework to do. So now let's compute this. So we have a to b x f of x dx, which is going to be minus r to r, right? This point is r comma 0. This is minus r comma 0. Minus r to r x times square root of r squared minus x squared dx. Okay. Note that we could have done this directly in parametric equations as well. So now let's try to do this. Notice that the inside is an odd function. Okay. I mean, we can go ahead and do substitution and calculate it, or we can notice that this is an odd function. The integral from minus r to r of this is going to be. So that's where odd function comes handy. Now, for to compute my, we do the following integral half f of x the whole square dx. Of course, my has also rho multiplied to it, right? Recall my formula is half a to b rho f of x square, but we are computing directly y bar here. So for y bar, I need this integral half f of x square dx, and then I'm going to divide it by 1 by a at the end. So, so here we get half. This is going to be integral a to b. So we have again minus r to r minus r to r of half r square minus x square dx, right? Because when I square it, the square and square root will go away. Now note that this is an even function. So I can write this as 2 times 0 to r half r square minus x square dx. Okay. So we get 2 times 1 by 2. They cancel out, and inside the integral is going to be r square. Integral is r square x minus x cubed by 3. The limits are 0 to r. And that can be seen as these 2 and 2 will half will cancel out. And we put upper limit, we get r cubed minus r cubed by 3. And when you put the lower limit, it's 0. All of them are 0 essentially. So we get 2r cubed by 3. Okay. So therefore, let's see what is our x bar and y bar. So x bar is whatever integral we computed by a, which is 0. Y bar is this 2r cubed by 3 divided by area, which was pi r squared by 2, right? Half of the area. And that is going to be 4 by 3 by 4 by 4r. So this is where my center of mass is. If I consider this It will be somewhere here, right? This is where my x bar, y bar lies, according to our calculation, right? Because x bar is 0 and y bar is this. All right, so now let's look at another exercise. Exercise we had earlier, which was find the centroid of the region enclosed by y equals to x and y equals to x squared. Okay, so we have, this is the red one is y equals to f of x equals to x. And we have, let me just change the color of this. Let's just keep this red. And this one is going to be, the other one is, say, y equals to g of x. Well, let's keep this as, so that we know. Okay, so now, so let's find out the area first. So area is going to be 0. So this point of intersection is 1, 1, right? Area is going to be 0 to 1 of upper curve minus lower curve. So x minus x squared dx, which is going to be half x squared by 2 minus x cubed by 3, 0 to 1, and that turns out to be 1 by 2 minus 1 by 3, which is 1 by 6. Now, x bar. Now, it is interesting to note that x bar is going to be 1 by a, 0 to 1. Now, earlier it just had f of x, right? So here we'll have x times f of x minus g of x. This is an exercise. You should see why is that the case. Again, it will follow from the following that you are now looking at this piece, right? So which is upper curve minus lower curve. So f of x minus g of x, right? While doing the Riemann sum business. So dx, and that's going to be, so 1 by a, so 1 by 6, 1 by 1 by 6, that's going to be 6 integral 0 to 1 x times f of x is going to be x squared minus x cubed dx, which is going to be 6 times x cubed by 3 minus x to the power 4 by 4, 0 to 1. That's going to be 6 times 1 by 3 minus 1 by 4, which is a half, which is 6 by 12, which is half. Now let's do the similar computation for y bar. Now y bar is going to be, again, 1 by a, integral a to b. Now y bar was half f of x squared, right? So now in this case, because we'll have f of x squared minus half g of x squared. And again, this is exercise you should see. Again, the idea lies from the fact that you are doing upper curve minus the lower curve here, right? So we have 1 by 6. So integral 0 to 1 half x squared minus half of x squared the whole square dx, which is going to be 6 integral 0 to 1 half x squared minus half x to the power 4 dx. That is going to be 3 times x cubed by 3, x to the power 5 by 5, 0 to 1, so 3 times 1 by 3 minus 1 by 5. So I do this, so 5 minus 3, 2, so 2 by 15, 2 by 15, and then you multiply that by, so 6 by 15, which is 2 over 5. So these are x bar, y bar. So x bar is 2 by 5 is say 0.4, and x bar is 0.2. Right. So if I want to draw this, just say suppose I'm interested to draw this. So if this is 0 to 1 here, then x bar is 0.2, so 0.2, and y bar is 0.4, so somewhere around. Sorry, half is 0.5, my bad, not 0.2. My apologies. So it's going to be 0.5. So it's somewhere here, actually, which makes more sense from the physics perspective, right? So half here, 1 by 2, and then 0.4, which is somewhere. This is my x bar. Okay. So that's all, folks. Thank you very much.